Hi guys, today we are on page 56 in your packet and we're going to talk about solving exponential equations. So we've talked about solving linear functions in Algebra 1, quadratic functions, other polynomials, we've seen rational functions, we've seen radical equations, we've solved all these different types of equations. Now we're going to look at solving exponential equations, and then the last thing that we'll look at in this unit is solving logarithmic equations. So remember, for an exponential equation, that means the variable is in the exponent of my function. That means somehow, so an exponential equation would look something like this. That means somehow we're going to have to get the variable out of the exponent. That's going to be our goal, okay? Something that's not an exponential equation, like let's say maybe a quadratic equation, we wanted to get rid of the exponent to get that variable by itself. Here, somehow we have to get the exponent out, or the variable out of the exponent. So that's what we're going to look at. What options do we have to do that? One option is to equate the exponents. So that means that I will have the bases be the same number. And then if the bases are the same number, I know that the exponents have to be equal. In some cases, I've got a function where the bases are already written as the same number. In examples like the first one I'm seeing here, I'm going to have to rewrite them so that they have the same base. So 8 and 16 are not the same number. 16 is not a power of 8, but 8 and 16 are both powers of 2. So 8 I could write as 2, and 16 I could write as 2 to the 4th. So I can express them as powers of the same base. If the bases are the same, that means the exponents have to be the same. So remember our exponent rules, power to power means we multiply. So I've got 3 times 5x equals 4 times 3x plus 4. So I'm going to distribute here. So this would be 15x equals 12x plus 16. And now this is a linear equation. So I want to move the x's to be together. And I get 3x equals 16. And then divide both sides by 3 to get x by itself. And I'm just going to leave that as 16 over 3. So if I can rewrite the expression so that the bases are the same, I can set their exponents equal. Now this isn't going to be possible for every problem that we have. If I take a look at another example here, 3 to the x equals 14. There's not a nice way that I can write 3 and 14 with the same base. I would have to use a really goofy exponent. So instead of doing that, what I'm going to do is change this to its logarithmic form. So if I rewrite this in the log, this would be log base 3 of 14 equals x. And now this log base 3 of 14, that's something I can type in my calculator. So just as a quick refresher, if I pull up my calculator here, remember that the log key is the blue control option right above 10 to the x, which is down here. So log base 3 of 14 would give me 2.402, if we round to 3 decimals. So x is approximately 2.402. I can also, for a problem like 3 to the x equals 14, if I don't want to rewrite it as a log, I can take a log of both sides, and then we're going to use some of those log properties to help us get x out of the exponent. So you could take any log, but we're going to look specifically at common log and natural log. So this means that I am going to take the log of both sides. That means instead of 3 to the x, I want log of 3 to the x. Instead of 14, I want log of 14. Remember, log is an operation, so I'm going to do that on both sides. And now I get to use that log property that if I have an exponent, I can sort of throw it down in front. So I have x times log of 3 equals log of 14. And now I want x by itself. So I'm going to divide that log of 3 to the other side. And x equals whatever this is. So I'm going to type that in my calculator here. Let me bring it back up. And this would be log, since I don't see the base on my paper, that means that it's 10. So log base 10 of 14, let me get out of that argument there, divided by log base 10 of 3. Okay. Make sure when you hit enter on your calculator, you actually see your log divided by your other log and not 14 divided by 3 in that argument there. But this gives me 2.402 if I round to 3 decimal places. This is the same equation, I just solved it in a different way, so it should make sense. I got the same answer. And then another option that we have, this is sort of the same idea as what we just did, but instead of taking a common log, we could take a natural log of both sides. So that would be the natural log of 3 to the x equals the natural log of 14. And again, that exponent rule tells me I could throw this guy in front. So I would have x times the natural log of 3 equals the natural log of 14. I want x by itself, so I'm going to divide both sides by the natural log of 3. And I would get x to be, let me put this one in my calculator. Let's see here. So for natural log, that's blue, and then the e to the x button. So natural log of 14, get out of that argument, divided by the natural log of 3, and we get 2.402. Again, it's the same equation. I just solved it using a little bit different strategy, so it should make sense. I got that same answer again. And then just like every other function that we looked at, you can check your solutions using a graph. So let's check this guy using a graph. So if I pull up a graph here, I'm going to graph the left-hand side, which is 3 to the x. So 3 to the x. And then hit the tab key so I can graph the right-hand side, which is 14. And let me pull this up here so I can see that intersection. And then menu, analyze graph, intersection, click on either side. And that x value, 2.4, we don't get as many decimals on the graph, but I get the same solution, 2.4. Okay. So let's take a look at a few more examples solving our exponential equations. On the next page, at the top, this we can solve by equating the exponents. 27, I could rewrite as 3 to the 3rd power. So instead of 27, I'm going to use 3 to the 3rd power. And now the bases are the same here, so I can set the exponents equal. So x minus 7 equals 3 times 2x. So x minus 7 equals 6x. I'm going to move the x's to the same side. I get negative 7 equals 5x. Divide both sides by 5. And I get x to be negative 7/5. Or if you like the decimal version better, negative 1.4. Our next example, I'm going to solve by converting it to a log. Before I can rewrite this as a log, I have to have the thing with the exponent by itself. So I need to move this 4 to the other side to start. So 6 to the 2x minus 3 equals 17. Once the thing with the exponent is by itself, I'm not multiplying it by anything. I'm not adding or subtracting anything. Once that's by itself, I can rewrite this as a log. So this would be log base 6 of 17 equals 2x minus 3. I'm going to end up typing this in my calculator, but I want to do that at the very end so I don't lose any precision. So I'm going to sort of unravel this to get x by itself. So that means I'm going to add 3 to both sides. So I have here log base 6 of 17 plus 3 equals 2x. Notice that I'm adding 3s onto the log. I'm not adding it into the 17. It's separate, okay? So this log base 6 of 17 is its own number. I have to add 3 to whatever this number is. I don't want to do anything with the argument or anything with this. I'm leaving those alone. And then my last step, divide by 2, means I'm going to divide this entire side by 2. And now this is what I'm going to type into my calculator. So let me pull up my calculator, and I want a calculator page here. And since this is going to be kind of a bigger fraction, I'm going to do control divide so I get that fraction. And we want log base 6 of 17, and then out of the argument plus 3. And then on the bottom, I'm dividing by 2. So I get x to be approximately 2.291 if we round to 3 decimal places. And I typed it all in at the end, that way I didn't lose any precision. If I round in the middle of my problem, my answer isn't quite as exact. We're also going to look at some more examples where we take a common log and a natural log on both sides. We looked at with our earlier example how each of these strategies is going to give me the same solution, but there are times when it's nice to take a common log and when it's nice to take a natural log. It's nice to take a common log when the base is 10, right? When I already have a common log, because remember the base is 10, so this would be 10 to what power equals 10? 10 to the first power. So the common log of 10 is 1. So it's nice to take a common log when the base for my exponent is 10, because log base 10 of 10 is 1. For the same reason, it's nice to take a natural log when my base is e, because remember the base for natural log is e. So I'm saying e to what power would give me e? Well, e to the first power. So this simplifies to just 1. It makes my work a little bit easier. So up here, we're going to solve this by taking a common log of both sides. Before I can do that, again, I have to get this thing with the exponent by itself. So this guy right here, 10 to the x, needs to be by itself. I'm going to start by adding 16 to both sides. So I get 0.3 times 10 to the x equals 51. Then I'm going to divide both sides by 0.3. Again, I want the thing with the exponent by itself. So now I would have 10 to the x equals 170. And now we're going to take a common log of both sides. So this would be log 10 to the x equals log 170. Now that exponent rule kicks in, so this guy comes down in front. And I'm going to divide by this log of 10 on both sides. Now, if you don't remember this, that's fine. You're not going to get it wrong if you type this into your calculator. But if I remember that the common log of 10 is 1, I save myself a little typing because this piece is just 1. I actually don't need to divide by it in my calculator. I can just find the log of 170. So I get x to be, if I find the log of 170, pull up my calculator here. Log base 10 of 170 gives me 2.230. I round to 3 decimal places. If you did type in divided by log base 10 of 10, you're going to get the same thing because your calculator knows that this is 1, but it saves you a little time, saves you a little typing if you remember that too. And then we're going to see something really similar for our last example here. So we're going to take a natural log on both sides here. Before I can do that, I need the thing with the exponent by itself. So my first step is to move this 1/3 to the other side. So I get 2/3 e to the 4x equals 4 minus 1/3 would be 3 2/3. And then I'm going to divide both sides by 2/3. To simplify over here, I'm going to change this to an improper fraction. So this would be 9, 10, 11 over 3. And then when I divide by a fraction, we know that we multiply by the reciprocal. So I would get 11 over 2. E to the 4x equals 11 over 2. or 5.5, if you like the decimal better. And now that I have the base for my exponent by itself, I'm going to take the natural log of both sides. So natural log and natural log. Again, my exponent property kicks in here, and that 4x can come down in front. So this isn't in the exponent anymore. And then remember that the natural log of e is just 1. So this part right here is just 1. So what I really have is 4x equals the natural log of 11 over 2. Divide both sides by 4 so that I get x by itself. And then this part, I'm going to type in my calculator. Bring my calculator up here, and we've got, let me do my fraction again here. We've got the natural log of 11 over 2 divided by 4, and we get 0.426 when we round to 3 decimal places. Okay. And then remember, you can always check your work with a graph. So graph the left side, graph the right side, and look for your intersection. If I take a look at that with, we looked at a log problem before, let's take a look at that with an exponent on both side problem. Let's check our solution here. So if I pull my calculator up and I go to the graph, I'm going to go ahead and delete this. And let me graph the left side, that was 3 to the x minus 7 power. And then I'm going to hit the tab key again and graph the other side, that was 27 to the 2x power. And I don't have a great picture here, so I'm going to adjust my zoom. Let's try a zoom fit, see what that gives us. Okay. We can see down here somewhere, we should have a solution. You're very close down here. So menu, analyze graph, intersection. I'm not sure exactly where. So let's just do all that entire region. I'm zoomed out so far that I'm just going to shade that whole huge region. And there's our intersection, negative 1.4 from our graph. If I check the work I did, negative 1.4. You can always check your algebraic solutions with your graph. So again, 3 big strategies for solving exponential functions. You can equate the exponents for some problems. You can convert to a log for problems where you can't equate the exponent, or you can take a common or a natural log of both sides.